Oh,
Hi all. So I wanted to start by just acknowledging the fact that everybody the world over is going through an extremely difficult, challenging time. And what this means is that many of us are finding it hard to indulge in our usual joy of just thinking about physics and cosmology and the way the universe works. It's a very challenging thing to do, to sort of have to now think about black holes when we're worried about the sort of everyday existence and the futures of our countries and our people. So I wanted to acknowledge that difficulty, but by the same token, thank the organizers for the huge amount of work that I know they've gone through to put this meeting together and to give everybody a space to sort of have an excuse to set aside the everyday physical realities that we're all stuck in and bring us back to the privilege of sort of looking out at the sky and thinking about the universe again. For me, it's been a challenge, but it's been helpful in some sense. So the title of my talk for today is Fast Radio Bursts and Cosmology, and I hope to explain to you some of the stuff I've been working on and what I find interesting, and hopefully there'll be some new information for all of you, maybe different bits of information. To start with, I also would like to just thank the National Research Foundation of South Africa and the Department of Higher Education and Science and Technology that are funding my research, and the University of Cape Town, where I am a research chair. And they've been immensely supportive over the years, and I wanted to just acknowledge that. So by way of motivation, the questions that I've always found most interesting since I began research have been those that connect between high energy physics and cosmology. So the very smallest scale physics that sort of play out on the night sky on the very largest scales and large scale observations. And so this is no different in some sense. I'm trying to use really, relatively, astrophysical scale objects to try and understand physics at a greater level, and then also using a large number of observations to learn something about cosmology. So another kind of motivation for why I am sort of interested in pushing this approach is that in the past, we might have said that cosmology was a field in concordance. Things were moving all in a direction of having smaller and smaller errors on our measurements, on our observations, and we were heading towards a precision era in cosmology. And I think the observations of the last year or two have been very jarring and have now put us into a state where we might actually be a field in crisis. And so that's an opportunity, and I wanted to look at that and see ways around that problem. I want to talk about fast radio bursts in particular because I want to propose them as a possible new standard measure and also study them as independent actors. So try to understand what is the physics underlying fast radio bursts, and in so doing, get some greater understanding and insight into physics itself. And so the overall motivation and message for my talk is that the sky is a fabulous experimental playground for high energy physics. And so if we want to understand some small scale pictures, we can use the very larger scales of the universe to do so. So of course, I think I've benefited greatly from a dialogue with high energy physicists and astronomers over the years. And I want to encourage others who are not yet doing that to do that. You chat to your astronomer friends, they pose problems, and before you know it, you have entire new research directions. So I think that's a good motivation. So many of you will have seen, all of you will have seen these images before. I think 3 years ago, the slide would have been pretty standard in a talk, which is that we thought that we were in a stage of concordance cosmology. We understand very well about 5% of the ingredients of the universe, and the remaining 95%, although they're poorly understood, we call them dark energy and dark matter, and we have sort of some kind of handle on how we measure them and might constrain various theories for them. On the high energy side, on the particle physics side, we have our beautiful table of particles, the fermions and the bosons, and we pretty much understand well what are the ingredients that make up that 5%. So we were in a state that would be comfortably called concordance, but things have really changed over the last couple of years. So just to sort of follow through on how our theories of cosmology are built, I call this the known knowns. You will probably know the reference. Of course, it goes back further than the reference you may be thinking. I leave it to you to look up on Google if you're not sure what known knowns refers to. But the knowns of our theory were basically we need 4 inputs. 2 are the theory of gravity, so we need some theory of gravity, and the second is some theory of matter and its non-gravitational interaction, so everything other than gravity. Our best bets and our input into concordance is Einstein's theory of GR, and our best input for matter is the standard model. So you put those 2 together, okay? And then we need to make some sort of bigger choices. These are not given to you by the theories. GR does not give you a choice of geometry, and it does not give you a choice of topology. So we need to make those as choices that we input onto our theory. So the choice of symmetry of geometry is perhaps the cosmological principle, so an elevated version of the Copernican principle, the fact that we do not live in a special place in the universe is homogeneous and isotropic. And a choice of topology is not forced on you by geometry. You can have homogeneous and isotropic universes with different topologies. So you need to impose that as well. And of course, the data informs each of these 4 things, right? These knowns are informed by the data that goes in, of course, and there was some excitement about various topologies. So when I was a grad student, when WMAP came out. So those are the 4 sort of inputs. The known unknowns, these are the things that we know exist, we think we know exist, but we're not really understanding them so well, is really the dark universe. So dark matter and dark energy. So I have the sort of iconic images there of each. The bullet cluster is a great one for dark matter, and the rotation curves. These are things that, you know, everyone who's watching this video is likely very much in the known unknown category of the rest of us, right? You know about as much of these as the rest of us do. The thing is, everything we know about these kinds of things, everything we know about the dark universe is inferred from observation. So they're all indirect detections, pretty much like the state we were at with gravitational waves a few years ago, where we expected them to exist because of the indirect detection, but we had not yet directly detected them. So that's the status with dark matter and dark energy. There's been a lot of effort put into directly detecting dark matter. We should not kid ourselves. Lots of experiments have been done. We just haven't detected yet. That's not to say we won't. It's just that we haven't yet. Similarly with dark energy, it's a little bit harder to detect dark energy directly, but there are some possibilities of theories that have lab predictions for dark energy. I've been involved in those, not the topic of this talk, but there's a lot that you could possibly do there as well. So the thing is, each of these theories, dark energy and dark matter, require some kind of new physics. And I'm just going to take a tiny little detour because I think this is a story that is really worth looking at and reflecting on and gaining insights from. If you don't learn history and you don't understand history, I feel you have a very limited potential for your future. So it's worth understanding some of the history of people in astronomy and in physics, and that gives us some insight. So it also turns out that I spent the last 2 weeks learning about the solar system with my grade 2 child who's currently studying the solar system. And it's been really interesting to me, at least, to see the kinds of questions he asks, but also the things that are not necessarily well known. Okay, so for example, the fact that Uranus, the tilt is so extreme that it's almost spinning on an axis directly pointing to the sun. And the theories for why that may be, they're presented in the YouTube video to 7-year-olds as well known and understood. But it just happened that after we watched this video, the next day I saw on the archive a paper about, you know, people studying exactly this problem in Uranus. So there are many unsolved problems even in our solar system. And there's lots of exciting things to do. So the story of Urbain Le Verrier is a great one, okay? In 1846, he discovered Neptune. So the orbit of Uranus was not quite what had been predicted based on the other planets, based on celestial mechanics and looking at all of the other planets. And so he figured something was wrong. He worked it out, obviously, mathematically, pen and paper, like as was done at the time, and figured out that the only way to explain the orbit of Uranus was to propose another planet outside Uranus. So there needed to be another planet, and that planet was, of course, Neptune. He sent this off in a letter, and on the same day, the very same day that he got this that the letter was received in Berlin, they went to look that night, and they saw Neptune. So Neptune was discovered literally on the day that they got the prediction, and the statement was that it was discovered with the point of a pen. So Urbain Le Verrier discovered a planet with the point of a pen. And I think for 19th century physics, this was one of the greatest discoveries of the time. It was a huge deal. So before he had even started working on Neptune, he was also studying Mercury. So the fact that the precession of Mercury was not as predicted made him look for other planets that might possibly be between Mercury and the Sun. And I think it was until 1857 or so, so from 1843 to 1857, roughly, he was working on the precession of Mercury. So the moral there, of course, is the fact that you can spend more than a decade working on a relatively small, what seems like a small singular focused problem. And it's actually okay, right? You might get to a resolution, you might not, but the amount of time spent on a single problem, it feels like a luxury today, but actually I think this is how physics has often been done. So anyway, so he proposed that there was something, to explain the weird precession of Mercury, that there was something between Mercury and the Sun, possibly clumps of planet, or possibly a single planet. And the single planet solution had worked so well to explain Uranus, Neptune was such a great solution, that he figured there must be another planet on the inside, and he called that planet Vulcan, okay? So of course, we feel like everything we do is new, but Vulcan was not new. It came from whatever, nearly 200 years ago now. So the point is here is that there was some unknown phenomenon. He solved that problem by proposing a new object. A new object resolved the problem of what was missing, how the data didn't match reality. When he hit a similar problem, he used the same tool, right? He has a hammer, he just used it again, and it completely didn't work. You know, you will all know that that problem was not solved until a good 50 odd years later, more, when Einstein proposed GR, right? So like 60 odd years later, when Einstein proposed general relativity and showed that the problem was not in not having the right number of planets. The problem was having the wrong theory. So general relativity resolves that problem. The precession is basically correct in the predictions of GR. And so that really gives us a sense of the two ways we've solved problems historically. New theory, new object, right? And we've done the same thing with dark matter and dark energy. If you wanted to go and look at the entire literature on dark matter and dark energy, you'll see either proposals for why dark matter is just a new kind of object, dark matter, or we've got the theory wrong, like MOND, for example, right? We've got the theory wrong. Same with dark energy. Either it's a new kind of particle, or we've got the theory wrong. So the sort of simplistic way of looking at things has actually underpinned a lot of what we actually do in cosmology. And so, you know, of course, also it was only in having this problem that pushed either of them to a solution, right? So the problems are actually very good for us. So moving from this, I say the fact that we have this crisis going on with H0 at the moment, is it going to break our sense of concordance? It's possible, but it's also a huge opportunity for us. It gives us a chance to understand the universe better, to push us to think a little harder about cosmology, harder about how we take data, etc. So who knows what's going on with H0? There'll be other talks about this topic for sure. For me, it's just a motivation to think a little bit harder about what's going on in our overall concordance picture. Are there other cracks? How convinced are we about the evidence for dark energy? I don't know. The field itself has certainly started off as a philosophy. People looked at the sky, made stories, came up with ideas. There was a heavy basis of religion in how we thought about the universe on cosmological scales. It became a precision science, and now we're possibly in a state of crisis. So what are the solutions? Well, we can relook at existing data, and I think this has to be done. I think this is being done. It is just well beyond the scope of what I'm doing or am interested in. So people can relook at the data, the methods, the analysis, figure out maybe one of these experiments has gone wrong, made an assumption, something, okay? And that is clearly work in progress, just not by me. It's possible that there's new physics, right? Something else that's going on in the very early universe, perhaps more recently. And this is work going on in my group with Julian Larena and our master's student, Rebecca Hulliston. And it's important to sort of do a range of these things. And so it's good that that is happening. You could also look at a possible new theory of gravity, okay? Sorry about the 7-year-old in the background. This gives you a sense of what it's like to be a scientist in these times. Not right now, Meeks. Okay, so the option of a new theory of gravity is that it's possible that all of our understanding is wrong, and that we're building cosmology on the wrong theory of gravity. We can keep trying to test gravity using our standard tools of cosmology, but the problem is we're sort of stuck within this framework and we might keep reiterating the same mistakes. So another possible option, since we have this dawn of gravitational wave astronomy, is to use gravitational waves as a possible testing ground for theories of gravity, rule out possible theories, make other theories perhaps more likely, and then feed what we've learned back into cosmology. And my student, Irvin Martinez, is working very hard on doing this, and this is one of his sort of focuses. Again, it's not the focus of my talk. The focus of my talk is to look at different ways, completely different ways to probe distance scales in cosmology to try to resolve that tension. And this is work that before I started worrying about H0, for some time I've been building up with Tony Walters, who's a postdoc, was my PhD student some time ago, and Emma Platts, who is my current PhD student. So there are some examples from the literature. The first is, and this is using FRBs, I should say, okay, fast radio bursts. So the first is to try to constrain large scale features of the universe. So you can use strong lensing, you can constrain H0 and curvature, and using fast radio bursts, and the reference is there. The problem is you have to assume some priors, you need flat, and you need lambda CDM. And other options are to test the cosmological principles, so look for anisotropies on cosmic scales, and we can exclude a large dipole anisotropy with only a few FRBs. There's work there as well. So there's a lot that can be done, and I'm going to talk a little bit more about all the work that's being done on a cosmological scale with FRBs. But this is sort of some kind of motivation to say, well, H0 is a problem. Let's look at different ways to get a handle on it. So what are fast radio bursts? Sort of about time I explain. They're essentially transients. So they're not, meaning they're not there for very long. We don't observe them for very long. They were relatively recently discovered, only in 2007. And the field has gone through sort of rapid evolution. It's been absolutely fascinating to watch. There were a few of them, and sort of a year ago, there were maybe 30 or 40. And then suddenly there are hundreds that have been observed. And they're going to be thousands observed very soon, tens of thousands and more. The physics driving them is currently still unknown, though I think we're getting more and more clues over some of it. And the number of classes of fast radio bursts is also unknown. This is because the fact that they have really different behavior means it's possible that there are just multiple different classes, or we haven't yet observed all of them for long enough. So some of them have been observed to repeat, but not all of them. And I'll explain a little more about that later. So they're very bright on the scale of Janskys, and they're brief on the scale of microseconds. So, sorry, milliseconds, though you can get 100 microsecond. We do have observations at 100 microsecond scale as well. So there's a great possibility for new science and discovery with them. And I've done a couple of projects so far. The first was really a group exercise where Tony and I sat with, most of the students in my group, and we said, well, how about we work through all the current known theories? So at the time there were, I think, 47 theories, and maybe 40 FRBs had been observed. So the number was similar. And so we thought now's a good time to kind of go through all the theories and see what does each theory predict, and what observations could rule out each possible progenitor mechanism. And so we did this, and then we were extremely lucky to have Sriharsh Tendulkar join our project, because he brought with this wealth of FRB and astronomy experience to make sure that we got everything really perfect and correct. And now this is living on a wiki. It's called the FRB Theory Cat for catalog. And every time there's a new theory, we include the information, and you can see how each of them can be ruled out. So it's a very sort of organized way to understand what's going on in the field. The progenitor mechanisms, some of them are very esoteric, exotic, okay? So the cool thing is we can rule out some exotic physics, or put constraints on it, or maybe make plausible some of that physics. Some of it is cosmic strings, which is a little project that I looked at with my postdoc Renato da Costa Santos and Jake Gordon, who was my master's student and is currently a PhD student in Europe. And we looked at sort of, there were many papers that had already proposed them as possible cosmic strings, possibly driven by cosmic strings, and we looked at sort of how plausible that was. And you need to understand far more about the physics of cosmic strings and put in more ingredients to really get that correct. There are even more esoteric theories, including the fact that it's aliens sailing on light ships, sending light signals, sailing on ships, sending light signals. So I think there's a lot there's a lot of sort of theories that will not survive for very long, but that's sort of the point, right? You get data and you rule out theories. I soon turned to the possibility of, could you use them as cosmological yardsticks? And this had been studied in various ways, which I'll talk about as well. But this was a project with Tony, as I mentioned, my former PhD student, Brian Gainsler, who's a proper radio astronomer, Yinja Ma, and Amadeus Witzeman, who was also a PhD student at the time. And so we looked at the possibility of using FRBs as cosmological yardsticks, and I will talk about that in a moment. So the last scientific meeting that I went to before sort of the whole world entered into the stage we're in now was in New York at the Flatiron Institute, and it was an FRB workshop. Extremely exciting, stimulating. Every single talk was like great new science coming out. I've never sort of experienced a meeting like that before, and it was really kind of amazing. So I've tried to summarize what I remember of that, because sadly my notes are too far away for me to access. So the pulses themselves are roughly millisecond duration. So it's a very brief pulse. As I said before, the range can go from around 100 microseconds to 10 milliseconds, but we haven't really looked outside that pulse range. So it's possible that they exist in a far wider range of parameter space, but that's where we've seen them. The frequency, originally they were seen sort of in the 2 gigahertz range, but the frequency is now spread. So they've gone to relatively low frequency around 300 megahertz and all the way up to around 8 gigahertz. So they're in the radio and they're in the sort of wide range of frequency. Some of them are known to repeat. We've been looking for the period of those repetitions. Some of them seem to be periodic. Some of them do not seem to be periodic, right? There may be some pattern that we're not seeing yet. There's something very fascinating going on there, and we're not at the point where we can say we have a handle on it. They go out to at least low cosmological redshift, so they are definitely extragalactic. And that is kind of important, and it actually took many years before people were convinced of this. I'll explain a little bit later why we're certain of this, but the fact that they're coming from outside our galaxy is quite important, and it means we could possibly do cosmology with them. They're brilliant traces of their source environments, which I'll explain in a moment, and they tend to be, we expect them to be localized to host galaxies, which is not surprising, right? Matter clumps, you expect the matter to be where the other matter is, but figuring out the host galaxy is quite hard. It requires some kind of optical overlay or a counterpart, or there's some extra required effort. So we don't know where most of them are localized. We've only managed to localize around 5 of them. And even that's impressive. There was originally only 1. The last 4 or so have been relatively recent. When you localize them to the host, you can learn a lot more. Only a fraction of the parameter space has been observed. There's a lot more to do. And we expect tens of thousands of them per day going off somewhere in the sky. That is a very large number. If you think about the fact that we'd only seen a few between 2007 and 2017, the fact that there are thousands every day or tens of thousands every day tells you how we weren't necessarily looking in the right way. And I'll explain more in a moment as well. They have a varied polarization. So one reason that cosmic strings had sort of lost favor as a possible explanation is because of this polarization issue. But it turns out that some of them are linear, some of them are circular. It's possible, some of them are a mix. It's possible that the polarization is actually coming from propagation effects and not intrinsic. So there's a lot still to understand there. And really the crux is to try to detangle what are the host effects, what is the intergalactic medium effects, and how do you remove the big uncertainties in the dispersion measure, which I'll explain in a moment, that will allow us to do something with them. We don't know how far out they go in redshift. We've only seen them relatively close, but that's not surprising because you see the brightest things, the closest things are brighter, and it's harder to get further out in redshift. But if we see them very far out in redshift, we can do more, and I'll explain why in a moment. And lastly, there are a lot of theories, and it's possible that more than one theory is correct, right? These are not fast radio burst objects, more like fast radio bursters, so things that burst in the radio and are fast. And there may be many mechanisms that do that. That would not be surprising at all. So possibly the most important thing to understand is the dispersion measure. So a fast radio burst is this brief pulse in the radio, and it arrives with a delay that goes like 1 over frequency squared. Okay, the reason for that delay is because your photon is passing through a cold plasma. And so it's interacting with all of those electrons between the host and us, between where it's bursting and the observer. The dispersion measure contains the information about the distribution of electrons between the source and us. So if I were to put limits on the integral, it would be observer to source, okay? And you can also look at that in terms of time. So basically, it's an integral of the number of electrons between us and the source. If we have small dispersion measure, it means they're near. Because these objects have relatively large dispersion measures, that tells us they have to be extragalactic. And I think people worked very hard to convince themselves of this, and that the dispersion measure wasn't coming from something else. And that's pretty much accepted now. They appear to have a host galaxy, and they appear to mostly come from outside our galaxy, though they can also be within the galaxy, but most of them are extragalactic. So what is the cosmology you can do with them? And there are now dozens of papers on this. I've just pulled out a few, and I'm going to talk through little bits of things, hopefully to pique some of your interest and get you thinking about other things you could possibly do. And I would love to have these discussions with anyone who's keen, either in the formats that the organizers have created, or if you want to send me an email, that would be great. So the first one I've picked is an implication for the early universe, which is the epoch of helium reionization. So it's possible, so because FRBs probe the electron density all the way along path of propagation from the event to us, if they go all the way out to high enough redshift, they would be sensitive to helium reionization, okay? So you can then constrain that, but you need FRBs all the way out to above redshift of 5. So it's great, but it's hard to do. So observationally very hard to do, but interesting theoretically. The dark universe, right? The late universe, dark energy, lots of possible implications. And I've listed a couple of papers here. So if you have enough fast radio bursts in narrow redshift bins, if there are enough of them above a redshift of 3, and if you're able to ignore the host contribution, which is a big if, then you can constrain the equation of state of dark energy. So I will explain in a moment how the host contribution works, but the high redshift, getting a lot of them out to high redshift makes it easier to ignore the host contribution, and I'll reiterate that in a bit. So there's a possibility there. Another way to constrain the equation of state of dark energy is if you can have FRB GRB associations. So if you see them either that they're together, there's one event that caused both, or they're just at similar redshift, so they happen near each other. You look in the sky and you see them near each other. Then you can use the fast radio burst to pin down the dispersion measure for you, and the gamma ray burst to pin down the redshift for you. And using the two together, you can constrain the dark energy equation of state. And the math I'll do later on will explain for you why that should be. You can also constrain dark matter, right? The fast radio bursts will be lensed by dark matter. So for example, if you have machos, there's a mass range that they're limited to. They have to be above 20 solar masses. But if you have machos, then the FRBs will be lensed. They'll be both strongly gravitational lensed, and they can be micro lensed. And they'll give you different signals. So you would get, the same FRB you would see multiple times, and that would give you a more interesting time structure in your FRBs. Now, at first we thought FRBs had this simple structure, but when you look a little closer, they do have substructure. And so it's possible that double peaks of your FRB are really just the same FRB, but you're seeing it in two different sort of paths that it's taken because of microlensing. So you can constrain dark matter theories using enough FRBs, and that's also, really interesting. We can try to understand the origin of intergalactic magnetic fields. Here again, you use a combination of the dispersion measure, which I've explained, and the rotation measure, which really just tells you about how it tells you about the magnetic field between us and the object itself, for the intergalactic magnetic fields. And we should be able to distinguish between primordial sources versus astrophysical sources for the intergalactic magnetic fields. And so you can start to really understand far more about the physics in sort of intermediate scales between the FRBs and us by doing the study. But again, every single one of these papers has big assumptions. And I'm sort of highlighting them so that you are sort of cautious when you get too excited about what I'm saying. The big assumption here is that your progenitor has to be a neutron star. And so, or a magnetar, which is just a very, neutron star with high magnetic field. So those assumptions sort of go into it. This paper I found really exciting and interesting, which is that the kinetic Sunyaev-Zeldovich effect is very important for us cosmologically, right? It allows us it allows us to understand very well what's going on in the cosmological growth rate. We can get the cosmological growth rate, but the problem is there's this degeneracy with the optical depth. FRBs allow you to break that. You can break that degeneracy by using a large number of FRBs. The problem is you need a huge number of them localized. Remember, we've localized 5. Here you need 10 to the 5 localized FRBs. Possible that we will get that in a couple of years, but that's sort of required to be able to break that degeneracy. Lots of implications for fundamental physics. Not surprisingly, it's possible that if the photon had mass, then you would get a time delay between different frequency components, right? And the lower frequency components have a bigger delay. As you can see, there's a 1 over frequency squared pattern there, which is the same pattern as the dispersion measure. So this, the dispersion measure. So this would mean that we can constrain the possibility of photon mass from FRBs, but you need to know the redshift and you need to somehow be able to distinguish this from the dispersion measure. Similarly, you can use this time delay between subpulses to constrain the mass. There's the constraint base given on the theory above, and no, I can't use the arrow, sorry. And also on the post-Newtonian, the parameterized post-Newtonian parameter, gamma. So that is different photons of different energy, and you can see that you can get the strongest constraints can come from looking at the time delay between these subpulses. So you're effectively constraining the weak equivalence principle there. So this is, I think really interesting, exciting kind of things you can do. Finally, you can put together gravitational waves and FRBs. If they're at the same redshift, they don't necessarily have to be from the same source, but if they're at the same redshift, you can build a new standard siren by using the luminosity distance and the dispersion measure together to get a constraint that's independent of H0. And again, your problems there are the uncertainties in the dispersion measure that come from having an intergalactic medium. So there's a fortune of things to explore, and hopefully this is sort of an introduction for all of you, but you need to be very aware of the priors and the assumptions that go into what you're doing. So in terms of cosmology with FRBs, sorry, I saw a message which is a bit confusing. I wanted to talk about the sort of work that I've done and the relatively small contribution that we made. And I'll explain a little bit later how I got to thinking about it. But the question is basically, okay, you say you can constrain dark energy, can you constrain curvature as well? Okay, and so we're going to use the dispersion measure, as I mentioned before, as a probe. And the question is, can we get better low redshift curvature constraints than you can get from supernovae alone? Okay, in a minute. Okay, so the general cosmological picture is explained over here, and that is basically the dispersion measure. You need to average it over the redshift range. It's inhomogeneous, and so that is a huge problem. You need to average it over that range, but it's sensitive to cosmology because you have in that E of Z, you have all the cosmological parameters there. So omega matter, omega dark energy, and omega curvature all fit in there. And the K on the left-hand side, you can see, includes the baryon mass fraction. So that sort of, the K is basically telling you how much matter there is. It's omega baryon and the baryon mass fraction. And the chi is a combination of the hydrogen and helium mass fractions and the ionization fraction. None of this is surprising. Remember, we're integrating over the number of electrons in the column between us and the event. And so all of those ingredients involve how much stuff there is. The expansion rate of the universe is folded in there, and it's possible to allow dark energy to be evolving as well. So we can include a general function, or we can parameterize the equation of state, as is typically done with W0 and WA. So what are the different contributions that you get to the dispersion measure? I've taken the slide straight from Anthony because it was so nice. I didn't want to make my own. And really, there are roughly 3 contributions. The one is the contribution from the Milky Way, which is pretty well known from galactic pulsars. There's also a little bit from the halo, which I haven't included here, and is recently released work by my student Emma Platz with others. The other is the dispersion measure that comes from the host galaxy. So it has to get, the light has to get through the host galaxy first. And there's a huge amount of uncertainties there. That's where all the uncertainty really is. And then the stuff we want to extract, you subtract off those two, you extract the dispersion measure of the intergalactic medium. That's where all the cosmological information lies. And I'm sort of alluded to this before, but I didn't really explain in depth. If the host is very far away, the dispersion measure will be very large, right? You're going through a huge amount of material. But the contribution from the host will be relatively small. And so to limit that uncertainty, you want to look at very far away FRBs. That's why the very high redshift ones are more useful. But of course, we don't have as many of them. In fact, we don't have them yet. So that's just sort of an intuitive explanation that hopefully will make sense to you. So what we did, and this was a couple of years ago, is we looked at nearby FRBs, so up to redshift of 3, relatively nearby. And we simulated using a HIRAX-like survey. I'll explain HIRAX in a moment. We did a forecast using MCMC and combined that data with the existing data, the CMB, BAO, supernovae, and H0. And not surprisingly, we found that FRBs, they're not great at constraining anything in that range, in part because you want to get a constraint on curvature, but actually it's too recent. It's too short time scale. You need a much larger time scale to do that. And so, well, I'll get to that in a moment, but the fact that your FRB constraint, it's very large, that's the gray one, but it's at least orthogonal to existing CBSH constraints. So that was slightly useful, okay? But once you add those priors, you then get an improvement. And we found the biggest improvement was over on omega baryon, which is zero surprising. You could have predicted this in advance, especially if you were following the logic I'm giving you, because omega baryon is the number of electrons and you're sensitive to the number of electrons. So the fact that you're constraining, you know, the baryons is not at all surprising. The whole thing is extremely limited by the fact that we have a lot of uncertainties in the host, and in the IGM we have to average things, which is, you know, already risky. We wanted to look at constraining curvature, and you get terrible constraints with FRBs alone. But if you add the CBSH, you know, all the other cosmology constraints, then you get an improvement on omega baryon relative to omega curvature. Again, not surprisingly, because you're putting in the priors, and omega baryon is still the thing you're most sensitive to. And again, you're limited very much by your uncertainties. So what Tony eventually realized, I think I referenced the work before, but this was work really led by Tony Walters. What Tony realized eventually is that we were fixing FIGM. In all of this, we put in FIGM, remember, is the fraction of baryons, the baryon mass fraction, okay? We were fixing that based on the numbers assumed or used in astronomy. And the truth is, we don't really know what FIGM is. So I introduced here the missing baryon problem quickly in case you don't know what it is. Big Bang nucleosynthesis and CMB give you separate constraints of the total number of baryons, and they predict that they should be, you know, around 5% of the total energy density. And when you add them up, you only get 70% of that 5%. So adding up all the baryons that we actually see, you get 60 to 70%. So something's kind of wrong. There's about 30 to 40% are missing, and they're expected to be in the warm, hot intergalactic medium. And there are various kinds of observations that have made this more and more precise. But the point is that if we allow this fraction of baryons to be free, and you treat it as a free parameter, then all your constraints are now dominated by your priors, by the fact that you put in the CBSH as a prior. And so, you know, it was critical for us to actually fix FIGM, but not the right thing to do. In fact, the right thing to do is to take cosmology as the prior, the cosmological constraints, and then use the dispersion measure to constrain FIGM, which then resolves for you to some extent the missing baryon problem. Because if you get the right level of FIGM, that alleviates the problem entirely and tells you the correct percentage that are hiding in the intergalactic medium. And so FRBs are not surprisingly an excellent way to measure the diffuse baryons in the IGM. And so we sort of came to this nice realization. So I think I have about 15 minutes. I might have misestimated my time. So in the time remaining, I want to talk a little bit about the HIRAX experiment, which is the hydrogen intensity and real-time analysis experiment, which is led out of South Africa. We have wonderful collaborations with people all over the world, especially those who are working on CHIME at McGill and in Canada, but it's a South Africa-led project. And basically the idea there is that there will be an array, a 1024 dish array of 6-meter parabolic telescopes. They'll observe in the range from 400 to 800 megahertz. So it's a radio interferometer in that range, which is the optimal range for getting at dark energy. It gives you the redshift range of 0.8 to 2.5. And so we can do intensity mapping experiments of baryon acoustic oscillations, which will allow us to learn about dark energy. It will observe the unresolved sources using the redshift of 21 centimeter line. And we can make maps of the large scale structure of the universe and therefore learn about the expansion history. So the experiment is designed for dark energy, but it's also, the secondary science is as interesting as the primary science, which is that of transients. And I've sort of, landed up thinking about them a lot, as you've seen. And so FRBs, as I've described, brief, bright, radio transients. The experiment itself is entirely complementary to CHIME, which is already putting out absolutely beautiful FRB data, very exciting data. The main difference is that because we're in the south and we don't have snow, our dish design is simpler, and we can have parabolic dishes instead of cylindrical dishes. And we have very low RFI, which I'm going to show you why in a minute. So these are the forecasts. Amadeus did the ones on the left, my former PhD students, and on the right, those were done by Devon Crichton. You can see you get very nice constraints on dark energy and on the equation of state of dark energy if you break it up into that W0, WA parameterization. And there's some pictures of HIRAX and where it will go. The naming is not based on the metal band. It's based on the fact that we have the Karoo Array telescope. That's 7 telescopes in the Karoo, and we decided to make more of them. So in Afrikaans, meerkat is more of the Karoo Array telescope, but also the little animal that lives in the Karoo is the meerkats. And so because HIRAX will be living next to meerkat, we named it after the other animal that lives in the Karoo near the meerkats, HIRAX, which is the rock dussie, and hence the name HIRAX. So hopefully that little bit makes sense. So South Africa is a particularly stellar place to be doing radio astronomy. The government passed more than a decade ago now, the Astronomy Geographic Advantage Act, which means that there's no RFI, there's no radio frequency interference in this range across the Karoo. So people are not allowed to produce basically radio noise. And you can see that 400 to 800 megahertz range is absolutely precious and golden, and there's no sort of peaks around it. That corresponds, when you go into redshift, to that redshift range I described before, and you can see where HIRAX sits in that redshift range. So that's why that range. The primary science, as I said before, is intensity mapping. So measure the baryon acoustic oscillations with H1 intensity mapping, observe unresolved sources. You can go out to far further in redshift, and you can make a far better map of the galaxies, because instead of looking at the exact amount coming from each galaxy and studying each one up close, you're doing this kind of zoomed out thing where you look at the sort of, you do like an artistic impression, you do a map of the intensity, the brightness. And I've given this great artwork as the way that I personally understand this technique. So it's a Sunday on Le Grand Jatte by Seurat. And it was sort of, I think, maybe the pinnacle of pointillism, where basically instead of really painting the faces of the ladies looking out at the sea carefully or of anything, they're tiny little dots that when you zoom out and you look back, you get this impression. And that's all we actually need. All we need is an impression of how much of the intensity of H1 in these galaxies rather than each one. Why the BAO? Probably this is well known to most of you, but they set a preferential length scale, and from there we can characterize the rest of the history of the expansion and get at dark energy. So HIRAX itself will be largely based in the Karoo, but we've realized the power of building outriggers, and I'll explain in a moment why that's so exciting for fast radio bursts. And the outriggers are basically sets of 8 telescopes with the same design as the original, but very far away. So instead of having just this very close compact array, we will also have very large baselines. So some of them will be far away within the country and others in other parts of Africa. And the point is, by getting very large baselines, we can get at sub-arc second at very, very, very focused localization for fast radio bursts. Why is that important? Well, you get really significant increased resolution. So the arrays alone give you this arc-minute resolution. So I can tell you that the fast radio burst is somewhere within that galaxy, which is possibly fine. But if we can get sub-arc second resolution, then I can tell you where it is within the galaxy. So you might be able to pin it down and say, this particular FRB is somewhere towards the edge of that galaxy. And once we have tens of thousands of FRBs, we might be able to pick out a golden set of them that all live on the edges of their galaxies. And then we can remove the host galaxy uncertainty. So there's really a lot you can do by just beautifully localizing them, and you can get a lot more understanding into their origins, into their nature, what is driving them, but also the ideal way to use them for cosmology is to really be able to localize them. So I think I promised in the beginning that I would tell you the story of how I landed up thinking about these things. And it probably is one of those things that happens to many of us, which is it was a random conversation with George Ellis where he asked, can the SKA constrain the multiverse? And everybody sort of laughed and I think moved on. And myself and Chris Clarkson and our student Amadeus eventually started to talk about how you could do that. Of course, the multiverse, there's very many things within there, but one version of the multiverse is including eternal inflation. And we knew that curvature, getting a better handle, a better constraint on curvature, is a way to constrain the multiverse. And so we thought, well, is it possible that you could use the SKA to constrain curvature? But before the SKA, is it possible that we could use HIRAX or a HIRAX-like array to constrain the curvature? And so that's basically how I landed up thinking about radio astronomy, which is to try to get better curvature constraints. And we realized, I'll just give you a very quick summary, we realized that you can break the dark energy curvature degeneracy, which would then allow you to get better constraints. Of course, if you see a signature, then that's a different story, but the best we can do for now is get constraints. And the way you do that is you combine the 21 center emissions from many galaxies. You can survey a far larger volume, which I think I mentioned before. You can measure them out to higher redshift. And so you have sort of two options. The one is to consider a constant equation of state and just skip the dark energy dominated region entirely. You just go out to redshift 3, redshift 4, and you just look above there. And that's all curvature, right? You're done with dark energy. You couldn't do this without intensity mapping because we weren't able to get a high enough volume of galaxies that far out. The other option is to consider a sort of piecewise equation of state for dark energy and then use an MCMC to sample the posterior of the curvature, marginalize over the bins. And if you have enough bins, then your results should converge and you get a constraint. And so we do get, some improvement on the existing constraints. The existing Planck constraint, you can see it only exists for constant W. Planck assumes fixed dark energy and zero curvature. There is no, not zero curvature, there is no evolving dark energy with curvature. There's only evolving dark energy or fixed dark energy and curvature. So if you have a fixed dark energy, then your curvature limit is basically 52 times 10 to the minus 3. If you allow for that evolution, you need different experiments, and the HIRAX constraint is predicted to be much better. The proof was just for HIRAX, but it's true for all intensity mapping experiments. And I expect all of them will put out fast, better curvature constraints and possibly rule out parts of the multiverse. So we thought this was a sort of nice thing to do. So some takeaway lessons from studying FRBs. Firstly, I think it's really important to understand history. So the FRBs themselves were discovered using high time resolution data. So that means that you have very short time intervals when you're taking the data. If you average over a larger time, that little blip will just average to being gone, okay? And they needed a large number of frequency channels. Most of them were discovered in the past, not going forward, obviously, in archival data. And the historical point to take away is they were not found because of some technological innovation. It wasn't that somebody built some brilliant telescope that made us see this new object. It was because of a total attitude shift, a change in the way they were looking for them, the way they were looking at data. And so this attitude shift led to discovery, which I think is a really important message to sort of think about and take away with us. To see lots of them, you need technological innovation, which is what we're now already doing. But the point is that the initial sort of spark of discovery came from a mind shift rather than some great technological evolution. Another important message that I think may be common to astronomers but is new to me is that the first one or the first few are not representative of all of them. You know, the first one that was really well understood seemed so well understood. It repeated, it was localized, it was in a specific type of host. Something I haven't mentioned before is that the hosts so far that have been figured out are not all the same type of galaxy. It's surprising. So to think that because you've seen something that's representative is a mistake, right? Nothing is representative. You need a huge amount of data to decide what is expected. And I think that applies to what we're doing now, which is part of why I'm putting in these messages. The next is that when you have limited resources and limited data, you introduce bias, not just into what you understand from your science, but what you follow up on, which theories you follow up on, something we all need to be very careful about. And even when you see nothing, you need to keep searching, right? I think this is, if you're not seeing the messages for COVID, you should, right? This is what we are doing. Certainly in my country, we are looking for positives. We're not waiting for them to walk into the hospital. So in terms of fast radio bursts, in terms of science, we need to look across wavelengths, across different types of messengers, different parts of the sky for the data, for the localizations. The more data we get, the better chance we have of understanding things better. And if we cannot set aside our biases, we will always find what we're searching for and we'll miss what's really there. So I think that's very important. And if you want to worry about 5G, then you should worry about the RFI it contributes. I think that is the only negative of 5G. So there's a huge amount of potential for discovery. There are a whole lot of puzzles and ideas, and there's a lot still to be done. My own personal approach, it looks very much, this is not really personal, but it looks very much like magnetars are very likely progenitors. But from a Feynman perspective, anything that can happen must. So if a theory like charged black holes, black hole batteries from charged black holes, if a theory says that fast radio bursts can come from it, then if you don't see those fast radio bursts, that theory is in trouble. Or you're constraining parameters in that theory. So you need to actually do science here. You need to use what we observe to rule out things. And that, I think, takes a challenge and turns it into a great opportunity. And so there's a lot we can really do with FRBs. There are a lot of open problems. There are lots of things to think about. One thing I've thought about is how are they distributed across galaxies? If we can start to see the distribution, do they sit at the edges, the halo, the core? Are they evenly distributed? What does that tell us about the physics? How can we use that to understand cosmology? There's just a host of open and interesting problems. And I'd love to discuss these with anyone who's keen and is able to get their heads into this sort of space. And my final thought, I think it's possibly I don't know if it's a deep one or not, but it's a difficult time for all of us. And I think as hard as it is to focus on science, it's kind of our only way to take ourselves out of what feels like the everyday and be able to look beyond that and give meaning to everything that we're doing at a time when I think many people are lacking meaning. I know for me, it's been a very difficult time, and just sort of working on this talk has been incredibly challenging, but also a chance to sort of remember sort of who we are at heart and at the core. So finally, thank you again to the organizers for putting together this wonderful CosmoCon beta and involving me, especially because my kid's dream is to go to MindCon, so I can tell them that we'll be going to CosmoCon in future instead. Thank you.